Good morning, students. Let us continue and take on the next basic concept in our Verilog HDL, that is data types. Okay, Verilog HDL supports 4 values. Those values will be having different strengths for each and every value. Okay, now we are having here many number of data types. One is value set, strengths, nets and registers, vectors, real-time register data types, array, memory and parameters, followed with strings. We will be knowing out each and every data type one by one. Now, coming to the value set, the Verilog HDL supports 4 values, and these values are nothing but the levels 0, 1, X and Z. Each and every level is having its unique strength. Okay, normally we know that 0 indicates it is a logic 0 or a false condition, 1 indicates it's a logic 1 and a true condition, X, small x, it is an unknown variable or unknown state, Z is a high impedance or a floating state. Each and every level or each and every value here is having again 8 different strength levels. So what are these 8 different strength levels for each and every level or a value set is supply, strong, pull, large, weak, medium, small and high. That means these all 8 strengths are present for each and every value set here. Okay, and you may ask me a question. So among these all 8 different strengths, which is the highest priority and which will be the lowest priority? Obviously, the highest priority will be the supply and the lowest priority will be the high impedance, that is high Z. Now, this supply is always of type driving. Supply, strong, pull, weak, all comes under the category of a type driving. Whereas large, medium, small is coming under the category of a storage, and high impedance is simply a high impedance. Then how to remember all these things? In order to remember all these things, I just want to share you a simple notation such that this will be highly useful to remember all these things. Like for example, supply is there. What is the opposite for supply? Supply means we are supplying something. High impedance in your normal electronic circuits, whenever there are connections are missing in between the two terminals, you will be definitely noticing a high impedance is present, because as there is a no connection, and if there is a connection means definitely some supply is being carried out on that wire that is connecting two terminals, right? So triple one opposite is 0 0 0, and coming to here, strong opposite is weak and large opposite is small. So you can see here large 1 0 0, the opposite for 1 0 0 is 0 0 1, large opposite is small. In this way also you can remember this strength levels. Okay, now where and when we do use this value set and their corresponding strength levels, when does it comes into our actual usage? So whenever, if there are two signals, I don't know what are the two signals. I mean signals in the sense it is whenever I am having two different values, which may be a 0 1 or 1x or zx or 1 0 1x, whatever it is. Okay, you can take. So these two signals, whenever they are driven on some wire, okay, so two different signals are there here. I am having a single wire. So which signal or the which value does your wire have to accept comes into a picture. So at this time the strength of your value set comes into picture. That is, the stronger signal always prevails in nature. For example, if you are taking two signals of strength, let it be strong 1 is there and 0 is there, but 1 is my strong signal and 0 is my weak signal here. Okay, among these two, the strong one will always prevails. That means we know that the priority or the highest precedency will be moving from lower to higher. That means supply here is having a highest priority and high impedance is having always a lowest priority. Similarly, if I have to drive two different signals on a wire, for suppose. So let it be strong X and strong Z. What will be the result? I mean to ask you what the wire will hold or will catch. The result will be unknown because these two values, of course I want to drive on a wire, but I am again checking what is the strength level of each and every two different values. Okay, so this value level X is carrying strong one and this value level Z is also carrying the strong strength. Okay, so the resultant signal will be X, that is unknown. So in this manner it is values and the strengths are highly useful in analyzing your hardware wires. Next is nets. So what is this net? Generally we know that I am having many number of logical gates in my circuit and each and every gate are being connected with wires. These wires are nothing but nets only. So nets represents a hardware connection between the logical gate or a logical elements. So for example, if you are taking an AND gate, so the output of a AND gate is continuously driven by the inputs. Otherwise, I can say that a net have values continuously driven on them by the output of the devices that they are connected to. Okay, so let us assume I am having an XOR gate. Two inputs of your XOR gate are A and B, and my output of my XOR gate is C. So here the XOR gate is driving something that is being catched with a wire, and that wire we are giving the name as C. C is the wire. So wire or net both gives the same meaning. So here C is holding the value, or it is a net. C is a net that have values that is being continuously driven by the XOR gate here. Okay, so these nets are actually a 1-bit value by default, and they are declared explicitly as vectors. And by default it is a scalar quantity unless and until I define it exclusively or explicitly as a vector. Okay, so then what will be the default value of your net? The default value of your net is Z, that is high impedance. Why high impedance means if someone are not driving anything, XOR gate only, you can take here as an example. So there are no inputs, of course output will not be existing. So if someone are not driving anything means definitely the wire will not be having anything inside it. That wire will not catch up with anything. That means it is simply floating in the air, I can say. So wire, when it does comes into active mode, whenever a logic gate is supplying something, whenever the output of your logic gate is activated, only the output wire or a net will be comes into picture. If the output of a logic gate is passive, that means there is no action that is involved in the circuit or in the logic element or in a logic gate. Simply your wire or a net will not hold up or catch up with anything. That is why the default value of your net is Z. Okay, so I can use the for example for the syntax purpose wire A, because net comes under the category of a wire. So wire A, wire B comma C, wire D equal to 1-bit binary 0. That means I have taken a variable called D and it is of type wire, and for this wire I have this wire is holding a value that is 1-bit binary 0. So here wire or a net D is fixed to a logic value 0 as soon as I am declaring a D variable here. Okay, that is the difference. And net actually is not a keyword. We are using wire as a keyword. So this wire as a keyword, but it represents a class of data type, which may be a wire, band, var, triand, tri-reg. This all comes under the category of wire reg data type. Okay. Most frequently we will be using wire instead of net for declaring any nets. Wire is my data type. Okay, moving to the next category, we are having here the registers. So what are the registers here? Registers, they are some storing elements. They are the storage elements. By default, register is a scalar quantity unless and until explicitly I define it may be acting as a vector. So register represents a data storage element, and like 1-bit register you can take. And if for suppose if I place something in that 1-bit register, I may place a 0 or I may place a 1 or something in between 0 or 1, I may place anything, I don't know, whatever it is. So that value will be present in the register until and unless I place it some other value. So I can say that the register retains a value until another value is placed onto them. Now, value of registers can be changed anytime manually in a simulation, because whenever you are performing the ripple carry counter example, we have taken there reg reset comma clock. Okay, so I am continuously changing the register variable. What is the register variable? Reset and clock. So reset I am changing for some amount of seconds, and after some amount of seconds I am changing it to 1-bit binary 0, again sometimes 1-bit binary 1. So this is a process that is involved. Okay, so until and unless I manually do change, the register will hold its previous value. So this is about register. Okay, and the default value the register keyword will carry is X, because it is a storage element. I said that it may carry a logic 0 or it may also carry a logic 1. So for the thing, the default value that is present in the your register is logic X. Okay, so keyword we use here is reg, that is reg. This is about registers. And coming to the next one, that is a vector. So what is a vector? We know in our previous semesters or previous classes the difference between a scalar and a vector. A vector is nothing but it is a combination of many number of scalar elements. Okay, so why we are using in vector in our Verilog HDL? We discussed about wires and reg data types earlier. The discussion was maybe on scalars, and if we would like to declare them explicitly as a vectors also is possible. Vector is nothing but multiple bit width. If I didn't specify any bit width, I can call or I can treat it as a scalar variable. You can see here a is a scalar variable because I didn't declare it exclusively, because scalar net variable it is by default. And wire 7 down to 0 bus and wire 0 down to 7 bus. Okay, this bus is a variable and it is being specified with a multiple bit in width. That is why I am calling this bus as a vector. Then what is the difference between this bus and this bus? Why the representation here 7 down to 0 and why it is 0 down to 7 is 7 down to 0 if I represented in this manner is it follows a it follows a little endian notation, and where 0 down to 7 means it is following a big endian notation. Okay, so this bus is of 8-bit width capacity, and what is it is of type wire again. Next, I have taken one more bool as a variable, and this bool is a variable of type wire. That means bool is a wire I am having here. So this bool is no more a scalar quantity, it is a vector quantity, and the capacity or the width of this bool wire variable is 32-bit width. You can see here in the picture or in the diagram. So this is about vectors. Let us take an example for the vector. I am having a bus variable which is a multiple bit width. I cannot say it is a scalar, it is a vector. Wire 7 down to 0 bus, and here wire 31 down to 0, bus A, bus B and bus C. Reg 0 down to 40 virtual address. Here 0 down to 40 means it is following a big Indian notation, and the above two are following the little Indian notation. So Verilog HDL had provided me a additional feature. That means among all these, let me take if I am having here a 32-bit elements for my bool variable of wire. If I would like to access the MSB bits, some of the MSB bits, if I would like to access some of the LSB bits, or in between the bits, in between 32 elements, if I would like to access, that facility is also provided in our Verilog HDL. For example, bus is there, bus A, 31 down to 0 bus. Let me assume this is a bus instead of full bus. I am accessing only the 7th element. So bus A is there. Bus A capacity is how much bit width? 32 bit width. So 0, 1, 2, 3, 4, 5, 6, 7. This element I am going to access. This is the special feature provided in our Verilog HDL. And bus 2 down to 0. So bus 2 down to 0 means a combination of elements also I can able to access, like a bus of 2, bus of 1 and bus of 0. So 2 down to 0 here it is there. So 7 down to 0 of bus. It is a bus variable and it is multiple bit width. So I am going to access among the 8 elements, I am going to access the 3 elements, that is bus 2 down to 0, bus 2, bus 1, bus 0. So 3 least significant bits of the bus I am accessing here. Okay. So again, you shouldn't use this kind of a representation, bus 0 down to 2. Why? Because it is an illegal. Whatever the notation during the time of declaration I used, in the time of accessing also I have to use the same kind of notation. Like bus is there, it is following a little Indian style, and during the time of access also I have to follow the little Indian style only, bus 2 down to 0, and bus 0 down to 2 is a illegal syntax. This is what happens. And the very next one is register 0 down to 40 virtual address. This virtual address is a variable of type register and it is of 41 bit width. Virtual address 0 down to 1. Okay, so that means here the left part is always treated as an MSB, the right side part is always treated as an LSB. So I am going to access the two most significant bits in my virtual address register of 41 bit capacity. So this is about vectors. Now let us discuss about the integer, real and time register data types. So what are these integer, real and time register data types are? We know that register is a keyword, wire is a keyword, and they can be represented either in a scalar quantities, also either in a vector quantities. Then what is the use of the integer? So an integer is also a general purpose register data type only. We know that a register is mainly used for the unsigned quantities. Then there should be some keyword that is used to store the signed quantities. What is the keyword? Integer comes into a play role here. So an integer is a general purpose register data type that is used exclusively for manipulation of quantities or manipulating the quantities. and the keyword what we are using for the integer data type is integer itself only. Of course, I can use reg as a general purpose keyword, but this doesn't support for a signed quantities, for which it is more convenient for me to use an integer variable for some activities like counting purpose. Let us take. Okay, the default width for your integer is again machine dependent. So if I am using a 64-bit compiler or a 32-bit compiler, that means the default width is 32-bit or 64-bit capacity. So registers, of course, they store only a unsigned quantities, but here integer store both. That means integer can accept integer variable. I want to say here, yes, integer variable can accept both signed quantities as well as the unsigned quantities. So here I am having counter. This is a variable of type integer. That means counter is an integer variable. So I told you that it can also accept unsigned quantities. So initial by default I am during the time of declaration only. What I am doing here, I am setting the value for my counter as -1. So this is about integers. Okay, and the next keyword or the next data type in our basic concept is real. So what is the real numbers? You have studied in your schooling. Real numbers are again classified in two types. One is a decimal notation, and it also may be occurred in the scientific notation. So these real numbers and real register data types can be declared by using a keyword called real. So the decimal notation you can see here, and the scientific notation will be here. So I cannot store these two values in any register data type or in any integer data type, for which there should be some real, there will be some real, I can say that a real keyword should be used here. Okay, now what is this without real keyword? These I cannot store in the registers, because register directly cannot store these two, because it is in decimal notation and it is in scientific notation. This cannot be stored in the hardware or a register data types. Okay, now for which what I will be doing here, let me take an example. Real delta is the variable, it is of type real. That means delta always accepts the scientific or a decimal notation. Initial begin, I have taken here the scientific notation. That means delta variable is storing some scientific value. Here the second delta value is storing some decimal value and integer. Okay, that this is the purpose of real data type or a real variable keyword. And now let me take some randomly integer I. You know that integer can accept signed as well as the unsigned quantities. So I equal to delta. What was the previous value of your delta here? The last value is 2.13. So this 2.13 whenever is handed over to an integer variable called I, the integer variable will not accept any real numbers, so it just round off the value whatever being supplied by your delta variable as 2. I gets the value of 2 because it is being rounded off. And the very next one is time. Okay, so Verilog simulation in the time of ripple carry counter, I have taken $time in the $display syntax itself only. So $time whenever it is invoked, the current simulation time will be generated as an output. That is, I can say my Verilog simulation is done with respect to the simulation time. So exclusively we should use some keyword to get the current simulation time, where a time variable, a time keyword I am going to use here. because I cannot use reg keyword, integer keyword, or real keyword, or whatever some data types I cannot use to store the current simulation time of my hardware circuit. So exclusively there should be some time variable, that this time variable will be collecting what is my current simulation time. So for which the keyword what I am using here is time. Time is the keyword. And let me take with this example time ASC. ASC is a variable of time. It is a time variable, and this variable always collects what is the current simulation time, $time. That means it may be 10 seconds, 5 seconds, 15 seconds, or 45 seconds, or whatever it is. So time variable will be taking care of this current simulation time of your Verilog HDN. And it is you may ask me a question, so what is the default width for your time register data type is? It is simply a machine specific or the implementation specific. So the very next concept is arrays. So arrays are nothing but a combination of, it may be a scalar or it may be a vector, that is two-dimensional vector I can say sometimes, or it may be a single dimensional vector. Arrays are allowed, we can use the arrays for any of the data type, like for integer or for real, for a register, for wire data type, anything for every, sorry, we cannot use the wire, I think so. We can use, definitely we can, why not, we can use. So we can use the arrays for, like how vectors are used for register and wires, in a similar manner arrays can also be used for registers and wires, apart from them for integer, for time, for real, all these things also arrays are applicable. That is having a multi-dimension with any number of dimensions. Each element of an array can be used in the same fashion as how we have used the scalar or a vector, net or a registers. So you can see here in the example, integer count 0 down to 7. So here I am having count is treated as an integer variable, and this integer variable is of 8-bit width. Okay, but instead of calling all these things like this, I would like to say it is an array of 8 because 0 down to 7 means 8 quantities I am having here. An array of 8 count variables, because it is a variable of course. So count 0, count 1, count 2 up to count 7. So it is an array of 8 count variables. And next is reg bool 31 down to 0. It is nothing but it is an array of 32 1-bit boolean register values. That means from here up to 31, like this 32 quantities of 1-bit register variables I will be having here. So in this manner, and let us take one more example. This is checkpoint is some time variable. I can say it is a time variable. That means 100 time checkpoints I am having here. Okay, so starting from 1 to 100, that means 100, an array of 100 time checkpoint variables this indicates. Okay, because it is a time variable, not a register variable it is. And we can also, I said you that the array may be a single dimension, it may be a 2-dimension, or it may be even be a multiple dimension. So let me take with an example of a multi-dimension, that is 2-dimension here. Reg 4 down to 0, port ID 0 down to 7. So this port ID is of type reg, that means port ID is a register variable. And can I say now that this is an array of 8, because 8 elements are there, 8 port IDs. Each port ID is of, can I say it is 4 down to 0 means it is a 5-bit capacity. That means it is an array of 8 port IDs, and each port ID is 5 bits wide or wider. So similarly, for how we have accessed elements in a vector, I can also access the element in array also. So how to access the array? For example, count 5. I am going to access fifth element in my array. And checkpoint 100. I am going to access here 100 checkpoint. A checkpoint is a time variable. Port ID tree. Port ID tree means I am going to access the third port ID 0, port ID 1, 2 and 3. So I am going to access the port ID tree, all the elements in the port ID tree, all the 5 bits in the port ID of 3. So in this way I can able to access the elements for the array. So just understand the difference between the vector and arrays. And you may ask me a question, sir, is this representation is correct, matrix representation? This is illegal. Then is this illegal or is this correct? Is the question. Now for this one you need to answer this. Integer matrix 4 down to 0 and 4 down to 0. So it is your job. Why it is illegal, or 4 down to 0 or 0 down to 4, this representation is correct, or if you are having any idea, just you can comment on that. So, and we continue with the remaining data types or keywords in our basic concepts of Verilog next class. Okay, thank you and have a nice day.